Hello and welcome back. Today we're going to continue looking at vectors with section 6.4 and specifically the dot product. So the dot product is unique. We're looking at two vectors, and when we consider the dot product written here, u dot v, it's going to be the sum of the products of like components. So we'll multiply u1 times v1, that's a product, and then add u2 times v2 for the dot product. All right, so what we're going to do is practice some of these. You could pause the video if you'd like and try them out, and then check your answers. Okay, so here we have three component form 3, 4, and then the second vector is 2, negative 3. So the dot product will be 3 times 2 plus 4 times negative 3. So we'll just have 6 minus 12 or negative 6. So we can see that the dot product of two vectors is going to become a number or a scalar. All right, here you see that it's written in linear form, and we can rewrite it if we like, but we have vector u, which is 2, 2, and vector v in component form would be 1, negative 1. So the dot product would just be 2 times 1 plus 2 times negative 1. So that'll just be 0. All right, let's look at the dot product of u dot v. And here we have in component form, this would be 0, 4, right? Because the j is showing the vertical component. And then v I'll just write as 3, negative 2. So that dot product will just have 0 times 3 plus 4 times negative 2, or just negative 8. All right, let's look at some of the properties. So in a way, the dot product is, you could say, almost commutative. So the dot product of u and v will be the same as the dot product of v and u. The dot product of 0 and v will always equal 0. You can have the dot product of u and the sum of two vectors, and so it'll equal to the dot product of u and v plus the dot product of u and w. Now, if we're going to take the dot product of the same vector, well, that's just going to be the magnitude squared, because we know that that's, if we look at this dot product, it would just be the horizontal component plus the product of the vertical component. And so that really is the dot product. That's really the dot product here. So we know that the magnitude would just be the square root. So just the dot product would be the magnitude squared. Now, if we have a scalar, we just need to be careful because the scalar does not distribute. Remember, because we're getting a scalar with the dot product. So you can actually multiply the scalar with either vector and then take the dot product. All right, let's practice some of these. You can pause the video if you like and try them and check your answers with us together. All right, so we have u dot v times vector w. Now we know that this is going to become a scalar. So I'm just going to multiply this out. So we have 3 times, let's write this here, 3 times negative 2 plus 4 times 6. And then I'll just put w here. I'll multiply that later. So we get negative 6 plus 24, so that'd be 18. And then we know the vector w is 1, negative 1. So in component form, we'll have 18, negative 18. All right, here we're going to have u times 2w. And remember, that's the same as saying that's going to be a scalar, right? So that would be the same as 2 times u dot w. Okay, so you can do either way. So I'm just going to stay with this form here. So we have the vector u, and I'll just write it out. That's 3, 4. And then I'm going to multiply vector w by 2. So 2, negative 2. And so that dot product will just be 3 times 2 plus 4 times negative 2. And we'll just get 6 minus 8, which is negative 2. All right, so looking at the dot product of u with itself equals 7. So we're saying u dot u equals 7. And remember, we know, and I wrote b, that meant u. you remember we talked about this right here in number 4, that the vector, if we multiply that dot product with the same vector, we're going to get the magnitude squared. So what's going to be the magnitude? Well, the magnitude will be the square root of that dot product of u and u. So the magnitude will just be square root of 7. All right, now let's consider the usefulness of the dot product. And the biggest, most common use is to find angles, right? So we used, we're going to come back to the proof, but we're going to use the dot product and the magnitude and cosine to find the angle between two vectors. So here we have the angle, we want to find this angle, the vectors are -3, 0, and v is 1, 6. So if we find the dot product, that's just going to be -3 times 1 plus 0. And then the magnitude, when we consider the magnitude, remember we're looking at the horizontal component squared plus the vertical component squared, and the square root of that sum. So this will just be 3, because just 9, which is square root of 3. And then this is going to be a product here. And the second one we'll get 36, 37. So the square root of 37, right? We square that, we get 36, square that, we get 1, add them together, we get 37. So if I want to actually just use trig here, I could just use my calculator. I can figure out the angle. But you know right away that this is a negative, so this has to be in the second quadrant. So we know that that's going to be an obtuse angle. All right, so using your calculators, you can find that measure really quickly, and that's 99.46 degrees. Okay, so the last question here is asking if these two vectors are orthogonal. And so if we're looking if angles are orthogonal, which we can also say perpendicular, we want to see if the dot product is equal to 0. Now we're thinking, why is that dot product equal to 0? Well, remember when the dot product equals 0 and we're looking at the cosine, well then that's going to make a 90-degree angle, because that's where the cosine equals 0. And so if we want to, just as a quick refresher, just knowing what the value of the cosine is can tell you what kind of angle we'll have, right? So if when it's -1, well, that's a 180, right? When it's between -1 and 0, that's going to be an obtuse angle. And then between 0 and 1 will be an acute, and equal to 1 will just be 0. All right, so for this one, we're going to see, is this dot product equal to 0? So let me just multiply -12 times 5/4 and 30 times 1/2. And you can see that's going to be just -15 plus 15. So yes. Okay, now we're going to prove how to find the angle between two vectors. So you may have noticed that we're using cosine a lot, right, to solve for that angle. So we're going to use a law of cosines for the proof. So remember the law of cosines, if we have two sides and include an angle, we could find that third side. So the length of that third side, or the magnitude, would be equal to the length of u squared, or the magnitude of u squared, plus the magnitude of v squared minus 2 times u times v times the cosine of theta. Now I'm going to just simplify this part right here, so you can see what combines and is eliminated. So we know that v minus u, the magnitude of that squared, is the same as the dot product of itself. So v minus u and v minus u. Just going to put an equal sign there. And then if we want to use the properties, well, we know we can rewrite this as v minus u and the dot product of v minus v minus u and the dot product of u. So what I'm going to do is simplify this a little bit. So we have v squared minus u dot v minus u dot v plus u squared. And I'm going to just use these here so you can see the magnitude squared. And so if I write the other side, you could start to see a lot of things cancel out. So we have that u squared, v squared minus 2 u v, sorry, lots of lines here, cosine theta. All right, so I'm going to cancel out the u squared and the v squared, right? Those are going to cancel out. And then when I combine this, we're going to get negative 2 u dot v. And that's going to equal negative 2 times the magnitude of u times v times cosine of theta. So I can rewrite this as cosine of theta is going to equal negative 2 u dot v over negative 2 u times v, and that negative 2 can cancel. I should cancel it earlier, but we have the cosine of theta equals u dot v over the magnitude of u times the magnitude of v. So we're able to prove that with law of cosines. Well, I hope this lesson was helpful, and I'll see you all in class.